I am going to model and analyze based on one of the books that is similar to Rossetti's book, but is not open access. We have it in Zaragoza, but it's not open access. The system is consists in a machine that that can produce things. Never, it always has raw material to produce things, and sometimes it fails. And the states of the machines are either it is doing nothing, it is idle, state 0, or busy, state 1, or down after maintenance or whatever, that is state 2. The processing time is 10 minutes. This is deterministic, and what is random is the time between failures that follows an exponential, and the duration of the repairs. So here are with the colors for the next slide to identify the variables. Then the products are in a warehouse for where from where customers can retrieve the products, and the state in the warehouse is the number of available products at this K. And the policy is that well, customers demand a random quantity. When a customer arrives, maybe wants 1, 2, or 3 products, and the customers arrive separated some random inter-arrival time, as in the post office. And when there are not enough products, then there is some unsatisfied demand, and the customer is unsatisfied. So if I wanted to get say 4 products, and in the warehouse there were only 2, then I am not satisfied, and the unsatisfied demand is 2. There are 2 products that I couldn't get. And the policy, the replenishing policy, is that when the number of products is lower than a parameter or attribute that is little r, then the machine produces until the number is the warehouse is full. That is, the number of products is big R. Okay. So here there is a trace or a history of the system until time 165. With in the case the capacity of the warehouse is 5 and the threshold for replenishing is 2. We start at time 0, let's say in this case with 4 products. So the state of the system is 0, 4. That is, machine is idle, and there are 4 products in the warehouse. Another state could be 2, 0. That is, the machine is down, and there are no products in the warehouse. But we start with this state, and the random generator says that in time 35, a customer demands 3 products. So this customer is satisfied because there were 4, but the state now is as we have retrieved 3, we have only 1 in the warehouse. So the machine starts producing state 1, and there is only 1 product in the warehouse. 10 minutes later, we will go on working, because we are going to work until the warehouse is full, and we have 2 parts. 10 minutes later, 3 parts. 10 minutes later, 4 parts. And in this case, when the customer arrived, we had generated the next arrival, and the next arrival happened to be at 69. So before we produce the 5th product, a customer arrived, and this customer wanted 5 products, so got unsatisfied because there were only 4. So we have now an unsatisfied customer, and no parts, one product unsatisfied demand, and now the machine goes on working, and there are no products in the warehouse. 10 minutes later, of the start of the moment when we finish producing the 4th one. So here, not 10 minutes later than 69, but than 65, we finish producing that fifth product that was not on time. What a pity. And then we have 1. In 85 we have 2, and now in 87 it happens that the machine fails, because at the beginning we have generated the time of the next failure, and it happened to be here. So we have 2 parts and the machine is down, state 2. But the life goes on. So in 101, a customer demands 1 part and gets satisfied. Even if the machine is down, there was enough products in the warehouse. And in 119, the reparation finishes. So we go on working. We have 1. In 127, we finished the second, because we had started 2 minutes before the failure. So we had 8 remaining minutes to finish, and so on and so on and so on. It produces more and more, and we reach the end. Here in the top, you can see a graph where we see the status of the machine in this history, in this trace. It was idle, then busy, then down, then busy, then idle, and the number of parts. It started with 4, then went to 1, then produced second, third, fourth, arrived the customer that wasn't satisfied, 0, then 1, 2, then failure. Here is the failure, and here arrived a customer, 1, and here it is repaired, and goes on producing. Okay, this is just to get the idea of how the system works with one history. I hope you understood how it worked. Some statistics, time averages, what they say in some books, continuous statistics, are, for instance, the utilization, the probability that the machine is busy. That, just to refresh, is we are busy this amount of time and this amount of time divided by all this time. Then this goes to the utilization. Or availability is the amount of time that the machine was not down. So we were down this time, so the rest of all the time we were available. 1 minus the probability of being down, or the time it was up divided by the total time, is the availability. The throughput is the number of parts that we have served, products we have served in the whole time. And we are interested also in the distribution of number of products in the warehouse. You see here we have 4, 4, 4. This amount of time, these times divided by the total time gives this. Or here we have 0. This only in this moment we have 0. So here is the probability, the probability that we have 0 parts. And here we have an histogram with the different numbers that the distribution of the numbers that we have in the possible numbers of products in the warehouse. These are what they are called continuous statistics, and there are also discrete statistics or tally statistics or counting. And here the number of unsatisfied customers was 1 out of 3, and the unsatisfied demand was 1 out of 9. There were customers asked for 9 products and they got 8 of them. 1 they didn't got. I hope you understand the system. If you have a question about the system, this is time to ask before we go with the model. In which I am going to use these distributions for the inter-arrival time exponential with mean 30 minutes, the mean time between failures. This is the inter-arrival time, sorry, of the customer. So 2 customers each hour, and they ask from 1 to 4 products. This has to be an integer. The mean time between failures will be an exponential with the mean time, mean 2 days. It's 2 days in the average we have for a failure, and the time to repair is 3 hours more or less, is a Gaussian or normal that we have to take care that must be 0 because it doesn't make sense to repair something in negative time. Okay. And the performance indices that we are interested in are mainly the number of the unsatisfied customers and unsatisfied demand, that we want them to be low. We want them to be below 2%. Also, we want to know the throughput, but maybe you can guess that the throughput is going to be in customers, it's going to be 2 customers per hour because this is the arrival rate. So if the system is not is well designed, as many customers as they arrive, they will exit. Okay, so this is just for verification. If we don't have 2 customers per hour, something is wrong, or maybe the availability or the service time is too long and then they get blocked and then the system is not going to work. Then utilization and availability, part of the time that the machine is working, part of the time that the machine is up, and the distribution of, well, things that we have seen in the previous history, the distribution of the values. I want to do all this with the Jansim tool. And not only analyze it, but also I want to decide which is the lowest size of the warehouse. I have these options, and the lowest ratio between because the size is important. If I have a big warehouse, more money to build it, and more products that I have there, and it is costful. And if I have a very high little R, it means that I will be frequently ordering new parts. So usually, if I have a room, let's say for 20 products, I want to ask for new ones when I have only less than 10 or less than 5. This would be few orders to the factory. But if I do that, I risk stock breakage, stock breakage. That is be without parts and then not being able to give them to customers, and then they will be unsatisfied. Okay, so it is interesting that this is low but not too low, and the same with this, right? Okay, so with this, I am going to start with the model. If you have any question about the system or how it works, please do it now. And I will change to the tool. This is the slide. Now I am in the tool. Okay, no questions? Shall we go? Fine. This model you have in the Moodle course, the file of the model, so you can play with it later. One thing could have been building the model from scratch, but this would be too slow. Very boring. So I assume that you know that in Jansim you can add objects from here. So for instance, you want to add a server, then you get it from the model builder, and then you edit the next component, which is the weighted queue or whatever. And you have here all the things that the palette, all the things that you can use. So some graphic objects, probability distributions of lots of kinds. You have resources that we are not going to use in this case, but they are very, very useful for many models, and you will see models with them. And process flow that are generate the entities, the customers, production orders, whatever, and generators of entities, customer arrivals, sinks. When you finish with some process, then that entity disappears. it has some technical importance because I think a couple of years ago in Jansim, they changed things to make it even more efficient. Jansim is very efficient, and they changed what they did with entities that were weren't useful anymore. So when they went to async, instead of forgetting them, they reused them to save time to generate new pieces of memory. And it made a lot of things change. Well, maybe it is a little bit too technical. Sorry. Okay, here we have many entities, many blocks for the models. So the way of building a model is just drag and drop the things that you want to use and set the values of the attributes and so on in the input editor. But in this case, what I'm going to do is just to go through the model with more or less order and show you everything in the model, or almost everything, but the model is already built. All right. So we start with the representation of the warehouse, and in this case, I decided to do it with a bar gauge, that is a graphic object. This one here. I think you see, yeah, yes, you see the mouse. But because in all the entities, I can define attributes. So in options, I defined the attribute K, that starts to be 0. That is the number of parts in the warehouse. And I define it here. You can define attributes wherever you want. It is a modeler choice. And I use this one because it represents a filling of something. So the value for the filling will be the value of the attribute K of this entity of the warehouse divided by the value of R, the capacity of the warehouse. So if we are completely full, it will be all blue. If it is completely empty like now, it will be all gray. And in other cases, we'll have some amount of blue, right? We will go later on with the R that is in this part of the model. For now, you can assume that R is an attribute that is fixed, and it is 5. And the small r is 2. They are here in the model, but we will see that later, right? So here we have the warehouse. And now let's have a look at the customers. The customers are represented by an entity. This is a prototype entity, a customer. And in this case, this is quite typical. The customer has some attributes. One is the quantity of the number of products is going to ask for. And then a Boolean, whether it is she is satisfied or not, and the unsatisfied demand. If she asks for products and got only one, then the unsatisfied demand of this customer is 3, right? So we have defined the prototype customer, and then here are the arrivals of customers. And the arrivals, in this case, follow a distribution that is the inter-arrival time distribution. The first arrival is not at 0 time, but is when it happens to be, and the inter-arrival time. So in many cases, you have a first arrival in time 0 or something. In this case, it doesn't matter. And the customers will be called C1, C2, C3, C4, and so on and so on. This is the base name. The distribution, that are here in the, as I showed them before, the distribution is an exponential, and Jansim asks you to give the mean value of the exponential. You say that is a time unit. The exponential, the result is a time, and it says that is 30 minutes. All right, it could have been the rate, but they decided to have it with the time, with the mean value instead of the rate. Okay. You will see in all the random things the random seed, like these two here. They are not the actual seeds, but they are numbers. So if a number into distributions are different, the seeds are different, but you don't know which are the seeds. What is important is that all the random processes, all the random distributions and so on have different seeds, unless you want the numbers to be the same. That is quite uncommon. When you make a simulation, all these seeds are different. If you do another simulation, you can change all the seeds at once, changing what is called the global substream seed. So if you here put a number, then you have all the seeds. If you put another number, then all the distributions will change all the seeds. And this is useful for replications and scenarios and so on. Anyway, now it is very well resolved, and when you create, even if you copy and paste an entity, the seed is changed automatically. Okay. The next thing, a customer, when we create a customer, the first thing that we do with this entity is go through an statistics block. And this is quite strange in this case, but I show you. Statistics blocks are very useful as well. What they do is when an entity goes through, they sample something. And something is whichever thing you want to sample. It doesn't need to be an attribute of the entity, or it can be whatever you want. And in this case, what is sampled each time a customer goes through is the number K in the warehouse. And so we will have some measures of the number of products in the warehouse, but not at all times, but only when customers arrive. I will explain later what are we going to do with that, and it is something that has some Italian flavor. So this is a surprise for the end. Okay, we get this, and the statistics blocks. At the end of the simulation or during the simulation, you can see whatever you like about the variable you are sampling. You can have the average value, the time average value, the maximum, the minimum, histograms, anything, almost anything. Next, we go to an assign, and assigns are the places where you change the values of attributes. And here, what we do is we change the attribute quantity of the entity that is going through now. So this entity, the object that is in this entity, its attribute quantity. The value of this is going to be the integer part of the value of the distribution of quantities, because this means the number of products I'm going to ask, and it has to be integer. So, and I wanted them to be from 1 to 4. Here we have to put a distribution from 1 to 5, or if you want more precisely, 4, 9, 9, 9, 9, 9, 9, 9. So from 1 to 19999 is 1, from 2 to 29999 is 2, and so on. So you guarantee that you have the same probabilities for all the integer numbers, but you cannot have 1.5 products. You have to do the floor in this function here. The next thing we do with the customer is something artificial. I call it approach. It's like the customer approaching the desk, the shop assistant. It's a fixed amount of time when we will see the customer going through this delay. This is just to see the customers, because otherwise they go from here to here to here to here to here, and we never see them. So we will see them here for a while, and we will take the value of the quantity of the customer, the last customer going through here, in this text. This text shows the object that is in approach, that is the delay, the attribute quantity of the object that is in approach. This, we could write this only, but what happens is at the beginning, no object has gone through, and then we will have an ugly message. So we do this. The value is, if the object is null, then 0, else this value. And this is the way that conditional things are written in Jansim. So values are given a conditional expression. The conditional expression is condition, and then value if true, value if false. Okay? And the format is quite C-like. Right. Then in this is the most interesting assignment. Here is where we do the things that is getting the products, see if I am satisfied or not, etc., etc. So let's see the assign here. We can see it in the builder, in the equation, in the input builder. So first, we compute the amount of the demand that is not satisfied, and it is the maximum of 0 and the quantity I am asking minus what is available, right? So if I am asking more than what is available, then I have unsatisfied demand. And if I am asking less than what is available, then it is negative, and then I have 0 unsatisfied demand, right? Then the value of the number of the value of k, if there is unsatisfied demand, then nothing remains in the warehouse, and if there isn't unsatisfied demand, then the number of products is we subtract the quantity that the customer is retrieving. And here there are some attributes that are in another entity, in customers record, that we are going to see in a while. Here we accumulate the unsatisfied customers, and the number of unsatisfied customers is, if there was unsatisfied demand in this customer, then one more, and otherwise the same as we had before. The total demand is the demand that we had up to now, plus the demand that this customer, the quantity this customer was demanding, and the unsatisfied demand is what the unsatisfied demand up to now plus the unsatisfied demand of this customer. Okay, so you can write as many sentences like this as you want for the different computations. Okay, and finally customers are go away, are eliminated. But this here is where I decided to put the attributes, the unsatisfied customers, total demand, etc. Maybe you are thinking, why not put in the unsatisfied demand and so on as bar gauges and so on? It would be a good idea. So it is up to the modeler and the readability. In this case, I put them here, and I had some text for the number of customers, which are all the entities that have been processed by the entity sinks, that are the customers that have been in the system, the total demand, and the throughput is directly the number of the processing rate is one of the things that I can in all of the entities. I have many things that I can see. For instance, in this one, I can see here this one. Let's see one moment. The state in which it is, the working state, the state times, if it has been in several states, the total time, the working time, the processing rate, the number in how many entities I have processed, how many are in progress, and so on and so forth. So many things are just available without doing anything. We don't have to do any computation, just pick the corresponding value. The throughput is the case, and the unsatisfied customers is the number processed. Sorry. If I had, if there, because I don't want to divide by 0. So if I have processed some customer, then is the number of unsatisfied customers divided by the number processed, multiplied by 100. And if I haven't processed anyone, then I put 0 instead of not a number or something that would be very ugly. Okay, so here for the customers, and now go to the production. For the production, here I have an entity that is very silly, that is a production order. The production order in this case is just make one product. In other cases, maybe make this number of products or products of different types, and it would have attributes. In this case, it doesn't have. And then here I generate processing orders. But when this is not the case that they arrive randomly. So what I want is to produce, to generate a production order whenever the number of products is below a little r and not more than big R. So here I put a threshold that is something that opens or closes the functioning of this generator. Here in thresholds, I am using the product needed threshold that I am defining here. And the product needed is that the number is less than R, or the number available now plus the orders plus the machine working is less than R. So if I am sorry, or no, and I will generate orders from when I am below R to the point that summing up the products that I have in the warehouse plus the products that are being produced now, or the products that are in the queue, the total is the big number, because I want to stop asking orders, because I know that, okay, they are not in the warehouse, but they are being produced or waiting to be produced. Okay. Right, this is the generation of orders. They go to the queue, and the machine, when there are orders, produces. And the machine in this case is a server that is very silly. It's 5. I think I don't know why it was 10 minutes and now it is 5. I suppose I was adjusting the numbers. Okay, but it's deterministic time. It could have been any distribution, but in this case it's deterministic. And the other thing with the machine are the downtimes, the times when it is not available. And how do we model it? In maintenance, we say in this case, we have many kinds of downtimes. In this case, we are going to consider immediate maintenance list. So they are things that are done immediately, interrupting any work underway at present. So if the machine is working and then it comes a downtime, it stops and it goes on later. In fact, immediate breakdown maintenance or immediate breakdown list would be more or less the same. It's different if it is broken or in maintenance. So depends on what they say to us. You can have the same server or the same entity can have this different kind of downtime. So for some for maintenance, some for failures or whatever. The downtime is here, and the downtime entity, we have to say which is the distribution of the interval between downtimes, that in this case is an exponential, and which is the distribution of the duration, that is the repair time, that in this case is a Gaussian. And the Gaussian is mean 3 hours, standard deviation 30 minutes, and I had to add a minimum value of 0 hours or whatever, but at least 0 hours is necessary, otherwise we will have an error. Okay. Well, I added here the number of breakdowns, and less light, red when it is down, green when it is up. Not much interesting. When a production order goes out from the machine, it means that the product is ready. So what we do here is to increase the number of products in the warehouse by 1, and the production order leaves the system. So we have finished with all the process entities. Let me see if I forgot something to say. Okay, yes. You can see there are a couple of plots here to make it nicer. One is going to reproduce the history before. That is going to reproduce the evolution of the number of products, the K, and the status of the machine, 0, 1, 2. And the way to do that is, okay, we say in this case, the data source for the primary axis is the number k, the data source for the secondary axis is the machine working plus machine maintenance multiplied by 2. So if it is not working neither in maintenance, is 0. If it is working, 1. If it is in maintenance, 2. That are the states, right? The number of points, if we put little points, then maybe if we put a lot of points, simulation is slower because it has to stop. It has to generate an event to draw the new point and the new point and the new point. But if you put very little, then you won't see what you like to see. That is from event to event, some flat things. The status is constant. So in this case, I put 1000. And okay, you define, for instance, in this case, that the X time, the time axis is going to be 3 hours before to now, and the interval is 1, blah, blah, blah. Okay. And the other one is, okay, and yeah, well, the two axes, the primary axis, that is K, and the secondary axis, that is V. And the other plot, this is a history plot. It's a plot, what is here in graphic objects, a graph, what they call a graph. That is the evolution of something in time. And here, this other one is what is an XY graph. And in this case, I am going to represent the histogram of the number of products. Where I'm going to get this? From these statistics. In these statistics, I said that the histogram being width is 1. In these statistics, when I am simulating, I will have to have here the histogram being centers, the upper limits, and the beam fractions. And then I will get the beam fractions and represent them here. And so the data source for X is the beam centers of the histogram, and the height are the beam fractions. And what does it make sense to do this with the numbers that I get in these statistics? Okay, I am not consider this is an approximation. If I wanted, as I don't have an entity each time that I increase 1 or decrease 1, if I wanted to have a precise number, a precise computation of the evolution of the histogram of K, I should make the computations in the assigned blocks. Each time a new product arrives or departs, I have to I have to know how long, how much time it has passed since the last event. So I had to record the last event time and then increase the corresponding beam fraction. I could do that, but it's a little boring, quite a little programming. Another thing I could do is to this entity, the statistics, that is the number of K, putting it so that an entity that would be like a clock is going around and around and around with some delay. For instance, each second it goes through the statistics again and again and again. So I would sample the number of products in the warehouse every second, every fraction of a second I want. Okay, this is okay. But I will generate a lot of events artificially. And then I remember a property that is that Poisson arrivals sample time averages. So if something arrives to the system as a Poisson process like exponential arrivals, and looks at the system and sees the state of the system, this one after the other, they are seeing the time averages. So this is what I'm going to use. I am going to use that I sample only each time a customer arrives, I sample and I sample and I sample. And then I I collect the statistics from there. Okay. This property, Poisson arrivals C time averages, the acronym is PASTA. This is what I said before, that is, it was going to have an Italian flavor, and here it is. So I think I have seen everything. Yes. Okay. Let's spend a few seconds, a few minutes with a simulation. I start simulating at a slow pace, real time multiplied by 600. So it is the simulating in real time means that time is going to advance proportionally. So no, I am not going from event to event. This is nice for the animation. So I see things happen in a proportion to time, and I can make it faster or slower. So I start slow. Don't look at this. That is here. You see the status. Here the warehouse fields. Here a customer was asked to these two, and another customer last asked for. We had no parts, so we started working. When we are working, we are increasing the number, etc., etc. You see it, okay? And we are computing the throughput, the unsatisfied customers, the unsatisfied demand. We have only 9, 10 customers, so this is not yet very definitive, right? Something that would be interesting is to see what happens in a failure, but I don't know when it's going to be a failure, or I do. This is debugging, more or less, or I go to simulation, and in the options, I can say stop when the number of samples of the distribution of the repair time is greater or equal than 1. So the first time I sample the distribution for the repair time is the first time I have a failure, a downtime, and I will stop there. Okay, so go on simulating real time, no real time. This means as fast as possible from event to event. And here we are in a failure. First failure or first downtime. Now this is red. It is not working. We have some products in the warehouse. And here you can see the event list. One event that is draw something more in the graph, and then this in this time 125.25 and a customer will arrive. In 127.14 the machine will end the downtime, and in this time I said I wanted to simulate for 30 days, so in 720 hours the simulation will end. These are the next events, okay, and these are the past events. When I am in this case, I can advance from time to time. I can advance to the next time, the next time, the next. Sorry, I have to remove the pause, you know, otherwise it doesn't advance. Next time, next time, next time. You see that the next drawing of the state plot advances. So, and you see the plot here, it is showing the status 2 that it is also boring. So I am going to the arrival of the next customer, that is 125.25. So 125.25, and I run to that point at once. Okay, I am there. And now next time, here is the next customer, the customer number 265, who is asking for 3 parts. Okay, so and the next interesting thing would be, for instance, in some moment it will disappear from the approach entity, the delay, but then 126 we have another arrival. We could go there, or we can go directly to 127. That is the end of the machine failure. 27 dot 14. Okay, and now next time the machine is now working. we have run out of products, so we have to start producing, and so on and so on and so on. Okay, so this is the simulation. We finish it till the end. Okay, and then we get that. In this case, I have a very large numbers of unsatisfied customers and so on. Okay, here is everything that I wanted to have. Okay. The way of looking at the results is not only just watching for instance, the queue length average or whatever. I have it here. Queue length average, minimum, maximum, the times with 0, 1, 2, 3, etc., etc. But usually you have the idea that you want some numbers. So the numbers you want, you put them in the simulation run output list. And here I have put that I want the value of R and R, because when I do many simulations, I want to know in which scenario I am. Then the throughput, the percentage of unsatisfied customers, unsatisfied demand, the utilization, and the availability. And these numbers they are moving, and at the end of the simulation, they are written to a DAT file. The DAT file, in this case, is here, and is quite silly. Well, you show that this is some hocus pocus. That is that you have to put the numbers adimensional. So if it is a time, divide by a unit time. If it is a rate, divide by a unit rate, and so on. Okay, and the result is that I had almost 2 customers per hour in the throughput as expected, 26% unsatisfied customers, and so on. But this is only one line. It's not too amusing. How to do the thing with many replications in many scenarios. Now, here in multiple runs, we are going to say that we want to run 19 scenarios, 10 replications each. So for each scenario, 10 different random processes. And which are the scenarios? I have defined them here in a file that is scenarios.txt. That is the big R and small r. All the cases I am interested in. 5, 2, 5, 3, 5, 4, blah, 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 20, 16, all of them. Okay. And then the big R that I was using in this case is from scenarios, that is this entity, the value of row scenario number, first, two, third, fourth row, and the first value. And for small r, the scenario number, second value. Okay. And when I do this, I will do all the simulations, scenario after scenario, replication after replication, right? So when you are going to do that, that is when you have finished with your modeling and the animation and you are sure that your model is all right, what you do is, okay, is everything ready. Recommendation, close the graphics because it will go faster. Close the all tools. And now, well, save and run. Sorry, it was in the middle of a simulation. Now run. Sorry, I forgot to remove the pause. One moment. Things that happen. Here in the simulation. Wow. Here. No, here. I still have this pause time here. Okay. Again, sorry. close tools, simulate, and now it goes scenario 1, replication 2, 3, 8, 9, blah, 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 blah. And at the end, I will get a file that, well, I have put it here. Well, I will show you the file, but in the meanwhile, it's going slow. I don't know why this time. It goes sometimes faster and sometimes slower. Anyway, maybe because I am recording and all other things. The final result is see, yeah, my other process is interrupt. Is this is the summary. So here we have the scenario number and then the value of R, big R, small r, and then the throughput that I check that is always almost 2. Then this is the mean value and this is the interval, the half width of the confidence interval. And here we have the customer satisfaction of customers, satisfied demand, the machine utilization, and the machine availability. Okay. Here I am only seeing the summaries after the 10 replications. In each, you see that there are many hidden rows that are the particular data of the particular simulations that we will see in a while. But anyway, what I see here is that, for instance, when I get to 15 as a capacity with 12 as a replenishing value, then I have unsatisfaction 1.47% plus minus 0.45. This is lower than 2. And this is 1.31, 0.45. This is lower than 2. So this is okay. And from here down, all of them satisfy the condition. This other has 20, the capacity of the warehouse is 20, but the R value, the replenishing value is smaller, is only 10. So it depends on what you prefer. It is a little bit better. And here you have all the values of all the other the utilization and so on. Okay, and just a while the file, just to see it for a while, has this aspect. So you have for each scenario all the replications, all the values, and then the averages and the confidence intervals.